Okay, good morning. Am I audible?
Yes, sir.
Okay. Um, so let me begin by recalling what we did last time. So yesterday we discussed trigonometric functions um, in details. Still, there are a couple of things that I can uh, teach you about trigonometric functions, but I think we had enough um, now we have enough knowledge about trigonometric functions to continue our discussion. And if something comes up, I will remind you and I will explain you um, what that fact. Um, my computer is getting a little bit slow. Um, all right. Can you see my screen now? Okay, good. So what we did was we all know the usual definition of trig functions using right triangles. So, but it has a major drawback because we have to limit our range of angles uh, from 0 to pi by 2. So instead of that, we took a unit circle of radius 1, and for any angle, we have a unique point corresponding to that angle on the unit circle. Then sine theta is opposite side. Opposite side is this vertical height. So y coordinate. Cosine theta is the adjacent side. Length of the adjacent side will be a length on the x-axis. So this is basically what the definition is. And based on that, we can say a lot of things. We have the freedom to choose any real number as our angle theta. But keep in mind that in this setting, we are always using radian measure, not degree measure, not the degree measure. Always we are using the radian measure. Um, we had a lengthy discussion about trig functions. At the end, we learned the derivatives of trig functions. I take x to be my independent variable, not the x coordinate, but angle. Because we are used to write x for the independent variable. Now, so this was our one of the major results we discussed last time. Trig functions and derivatives of trig functions. Then we had another important result called the chain rule. Chain rule says us about differentiating compositions. Let's say you have a composition of two functions. To differentiate this composition, we start from the outer function. So if inside we have g, we start from this outer function. So we differentiate it. We don't do anything to inside. So this is what we do for the first time. We differentiate f. Then once we are done with f, now forget it, f, and go to inside. Inside we have g, differentiate g. Right? Now, this is how we differentiate the composition. If you had like three components, F, G, and H, we first differentiate F while keeping other two factors inside. Then we forget F, differentiate G, and still keep H inside G. Now, once we are done with G, then forget G and go to H and differentiate it. For example, let me write it. If it is something like F, G, H. To compute the derivative, that means to differentiate F, G, H. We first differentiate F and keep G and H. Then we forget F, differentiate G and keep H. Then forget G and differentiate H. So in this way, we can differentiate any composition of any finite many functions. So we do it like a chain. We first differentiate the first link and then go to the second link and can differentiate it, then go to the third link and differentiate it, and so on. That is why it is called the chain rule, composition of like a chain. I think I gave you enough examples, but let me remind you. Sine of x squared plus 1. The first thing is to identify outer and inner functions. The outer function is sine, inner function is x squared plus 1. So we differentiate first we differentiate the outer function sine. Derivative of sine x is cosine x. We don't even look at what is inside. Once we're done with the sine function, then we look at the inside. Inside we have x squared plus 1. For that, we can use the sum rule. It's a sum of two functions. Derivative of x squared is 2x. Derivative of 1 is 0. So the final answer is 2x cosine x squared plus 1. If you think about this initial function, it is a very complicated one. It's a composition of trig function and a polynomial function. We don't even know the shape of the graph of this function. We don't know pretty much anything about this function except these component functions. But still we can differentiate it using the derivative of these components. So it is the chain rule is a very powerful technique and it allows us to differentiate many functions. For example, I can give you many other examples. Think about x plus 1 divided by x square plus e to the power x. Then let's take the square root. So we have, again, this is a composition. Outside is the square root. And inside we have a quotient. So let's differentiate this. First thing is to differentiate the outer function. Square root means power 1/2. So bring the power to front, keep whatever inside. Then reduce the exponent by 1. So 1/2 minus 1 is -1. Now we are done with this outer part. And we need to differentiate the inner function. At this point, we don't need to worry about the square root. We have to deal with it. So let's go on now. Take this part and apply the quotient rule. So the quotient rule says if you have something like u divided by v u prime minus u v prime divided by v squared. Since there's a minus sign in the numerator, we have to be careful. We need to keep the order. Otherwise, we get a wrong answer. So, for this case, for this particular example, our v is x squared plus e to the x. So, this is our v. This part is our u. So let's take, let's apply the quotient. Let's keep x squared plus e to the power x, differentiate the numerator. Derivative of x squared, x plus 1 is very simple, 1 minus keep x plus 1, differentiate x squared plus e to the power x. Derivative of x squared is 2x plus derivative of e to the power x is e to the power x. Divided by x squared plus e to the power x squared. Now, if you want, you can simplify this. In the numerator, we have x squared plus e to the power x minus x plus 1, 2x plus a to the power x. In the denominator, I have 2 times x plus 1 to the power 1 half, x square plus a to the power x 3 half. If you want, you can simplify the numerator as well. I think this is good enough. Right? So sometimes you have to apply more than one rule to differentiate the same function. Here we have to use both chain rule and the quotient rule. Sometimes quotient rule and the product rule. Likewise, sometimes depending on the function you have to apply more than one rule. So you need to know all the rules. You cannot just learn the power product rule and the power rule and hope to differentiate all the functions. Um, so today we will study few other um, rules that allows us to differentiate more functions. Now, oh, by the way, before we move on to this new topic, I need to give you some examples to remind you why we are interested in derivatives. Remember, derivatives are all about uh, tangent lines. I hope you are still looking at my uh, rule, my writing pad page. So imagine a graph of a function. We talked about the tangent line, slope of the tangent line is measured by the derivative. So um, at a peak point, or local maximum like this, uh, or a valley point, that means a local minimum. Hmm, I guess it is horizontal enough. So these points at a local maximum or a local minimum, um, tangent lines are horizontal. So dy over dx equals 0. Those are called critical points. Critical points. At a critical point, derivative is 0. So one way to find out critical points, local maximums or local minimums, is to compute the derivative and look at the zeros. We differentiate the function, make it equals to 0 and solve for x values. And in addition to that, when the function is decreasing, when the function is decreasing, the tangent line looks like pretty much like this red color line segment. The angle between positive x-axis and this line segment is an obtuse angle. Oh, so as a result, slope of the line is negative. So derivative is negative. When the function is decreasing, derivative is negative. When the function is increasing, function is going up. We have the positive derivative. Increasing, decreasing, and critical points. So derivative helps us to identify all these features. It helps us to understand this point where the function is increasing, likewise points where the function is decreasing, and critical points. Even for complicated functions, this is the case. Let's go back to our notes. Where does the function if the power x to the power 4 minus 8x squared have a horizontal tangent? See, this function is very complicated. It is a composition of two functions. The outermost function is exponential function, and the inner function is a polynomial of degree 4. But still, we can apply the same principle. Use derivatives. So y equals e to the power x to the power 4 minus 8x squared. If you simplify this function by factoring x squared, you get x squared minus 8. Now you can see when x equals 0, function value is 1. When the value of x is square root of 8, again the exponent is 0, you get 1. So the graph will be looks very messy, but still we can complete the derivative. Let's differentiate this. Derivative of the outer function is e to the power whatever inside it. Then let's move to inside and differentiate it. 4x to the third minus 8 times 2 is 16x. We can factor 4x. That will give us x squared minus 4. We can factor this quadratic part again because it is a difference of two squares. So this is it. It's different. Now, to have a horizontal tangent line, we always need zero of a derivative. Horizontal tangent line means zero of a derivative. So the horizontal tangent line we have dy over dx equals to zero. Let's look at the derivative. The first factor is something of exponential of something. Exponential functions are never zero. If you remember the graph of the exponential function, it looks something like this. No matter what you substitute, no matter what you plug into the exponential function, it is always returns you something positive. Not even negative numbers, not zero. So this part is always bigger than zero. So it won't give us any zeros, but the other three factors will give us three solutions, three zeros for the derivative. So we get x equals 0 or x equals 2 or x equals negative. Remember, y equals e to the power x to the power 4 minus 8x squared. So when x equals 0, corresponding y value, you can compute using the function y equals, set x equals 0. That gives you 0, e to the power 0 is 1. When x equals 2, the corresponding y coordinate is, we need to substitute 2. 2 to the power 4 is 16 minus 2 square is 4. 4 times 8, 32. So what we get is e to the power minus 16. So here again we get the same value, e to the power minus 16, because even if you have a minus sign here, once you take the fourth power or the second power, uh, we don't see the negative term anymore, negative sign anymore. So at these points we have critical points. Okay, at those points we have horizontal tangent lines. We can do a little bit better actually. Remember, the derivative is e to the power x square minus x to the fourth minus 8x square times 2x, x minus 2, x plus 2. Now we can do a sign analysis. Let me make a chart. So x equals 0 is a critical point. then x equals 2 is a critical point, x equals negative 2 is a critical point. Uh, Let me take a point, um, yeah, below negative 2, that means smaller than negative 2. Let me say minus 100. If it is a minus 100, uh, this is negative, this is negative, this is negative, and this term is positive. So their product will be negative. So for a point way below negative 2, derivative is negative. At negative 2, it is 0. Now let's take a point between negative 2 and 0. Let's call it negative 1. At negative 1, this is still positive, negative, negative, positive. So the product of the plus, minus, minus, plus, that means plus. Now let's take a point between 0 and 1. Say 1. At 1, this is plus, this is plus. 1 minus 2 is negative 1. 1 plus 2 is 3, which is positive. So the product is again negative. Uh, Finally, let's take a very large positive number somewhere here. So this is positive, this is positive. Let's say for x equal 100, this is positive. This term is also positive. Product of four positive numbers is again positive. So this is how the sign of the derivative changes. Uh, let's see. If the derivative is negative, function is decreasing. At minus 2, you have a horizontal tangent line. Plus means function is increasing. So minus 2 must be a local minimum. And at 0, before 0 function was increasing, at 0 you have a local maximum, then negative derivative means function is decreasing. So my 0 must be a local maximum. And before 2 function was decreasing, that is why it has a negative derivative. And at 2 derivative is 0, horizontal tangent line. After that, function is increasing. This is how the function is behaving at those 3 points. Negative 2 gives you not only a horizontal tangent line, it is a local minimum. Mm. Mm. If you want, I can sketch the graph of this function. Uh, One more thing to notice is, let's say, if you say therefore for x equals if the x to the power 4 minus 8x squared, and let's compute negative x. It's negative x to the fourth power minus 8 negative x squared. It's again the same function. You might be wondering why I am doing this. I'm doing this to show you a very special property of this function. F of negative x equals f of x. If you remember, that means function is even. A function with this property is called uh, an even function. The the even functions are important because they are symmetric with respect to y-axis. If you have the function value at x and function value at negative x, both are same. The common value is this y value. Hmm? So the graph is symmetric about y-axis. We are going to use that symmetry as well. So at 0, we have a local maximum, which is 1. At 2, we have a local minimum. E to the minus 16. And again, at negative 2, we have e to the minus 16. You see, at 2 and negative 2, we have the same value. That's again a consequence of evenness of the function. And function is symmetric with respect to uh, y-axis. At 2, the function looks something like this. At 0, function looks something like this. At 1, function looks something like this. Now you need to slowly combine those three behaviors. And before negative 2, there is no horizontal tangent line. Derivative is always negative. That means function is always decreasing. It should look like this. And after 2, derivative is always positive. That means function is increasing. It goes something like this. My picture doesn't look like a graph of a symmetric function, but it is symmetric. I'm very bad at drawing stuff, but this must be a graph of a symmetric function. Let me try to correct it. Uh, I'm very bad at drawing stuff. All right, this is the graph of d to the power x to the power 4 minus 8x squared. See, at first we have no idea. We had no idea about the graph, but then using our knowledge about derivatives, we were able to sketch the graph. This is not the perfect picture, but we know how it behaves. Um, so in school, our technique was to make a table and substitute values like 0, 1, 2, 3, 4, and make a table and plot those points and join them by a smooth curve. But that technique doesn't won't work for functions like this. These are complicated functions, but still uh, we can plot them using derivatives. So derivatives are really helpful to understand complicated functions. Not only this function, you see now that we have the derivative of trigonometric functions, we can plot them and study them using derivatives. We can do the same thing for log functions. As soon as we know the derivative, we know a lot of things about the function. We can deduce a lot of things about the function. All right. Um, Next, we need to discuss about the derivative of inverse functions. All right. Derivative of inverse functions. Um, all right. Let's start with the non-inverse function. How about exponential function? Let's say y equals natural log of x. This is the inverse function in inverse of e to the power of x. So if y equals f inverse, then x is equals f of y. So these are inverses of each other. So when we have this relation, we can turn this into, uh, we can remove the log function and make it to a relation between something and the exponential function. And x equals e to the power of y. So same thing that we have in the right hand side written for log and exponentials. Now imagine we don't know, imagine that we don't know about the derivative of log function. Hmm? Now, using the derivative of exponential function, we can differentiate this second term, second relation. Let's take it and differentiate it. Hmm? Derivative of x is 1. So we are differentiating this. We are differentiating it. Derivative of x with respect to x is 1. Then think about this other part, e to the power of y. Y itself is a function of x. Y is natural log of x. So y is a function of x. And therefore, this is a composition of two functions. Outer function is e, inner function is y. Our goal is to differentiate the first function, y, natural log of x. So our goal is to find dy over dx. Okay, our goal is to find that, and here we have a composition of two functions, so we need to be careful. Let's first differentiate the outer function, e to the power 1. That's it. Then let's go and differentiate y, the derivative of y with respect to x. So what is that? So we have 1, and we need the um, derivative in terms of x, right? Because x is the independent variable. Even though we turn it to a relationship, we wrote x as a function of y. Initially, y is a function of x. So this guy over here, e to the power y is x. So because of this, dy over dx is 1 over x, right? We knew the derivative, but at that time I did not give you any explanation. I just told you the derivative is 1 over x, and I promised you to give an explanation later. You see, this is how we differentiate any inverse function. We can do the same trick for other functions like inverse trigonometric functions. Uh, I did not discuss about inverse trig functions yet, but now that we have this, we can differentiate uh, inverse trig functions. Let's see sine inverse x. So the idea is to write it in terms of sine, differentiate both sides. Left hand side is 1, right hand side. Derivative of sine y. So again, this is a composition. Derivative of sine is cosine. Derivative of y is dy over dx. Dy over dx is 1 over cosine, that means secant of y. But we don't like this because we need it as a function of x, not as a function of y. Let's look at this. I can use a unit circle or a triangle. For simplicity, I will use a triangle. So that says it's a hypotenuse is 1 for angle y, sine value is x. Sine is opposite divided by hypotenuse. So this is x. By the Pythagoras theorem, the adjacent side should be 1 square minus x square root. Then cosine is adjacent divided by hypotenuse. So adjacent divided by hypotenuse is 1. So the cosine is just 1 minus x square root. Secant is reciprocal of that. So reciprocal of 1 minus x square root. So this is the derivative of sine inverse. Um, can you quickly compute the derivative of tan inverse x? Can you compute the derivative of tan inverse x? Because I showed you two computations of derivative for two inverse functions. I think now you can handle this. Because write it as a uh, uh, relation between, right? This given relation y equal tan inverse x has a relationship in uh, relationship between x and y in terms of tan function, not tan inverse, tan function. Then differentiate it using uh, the chain rule. Mhm. All right. I think I have given you enough time for this. Shall we look at that? Let's see. I put some answers, and most of you got it correct. Some answers had some mistakes, but those can be improved. So the idea is to write this y equal, so x equals tan y, differentiate both sides with respect to x, derivative of tan is secant square dy over x, then dy over dx is cosine square y, right? Now, draw a triangle. You can use a circle, but it will be, you are just making things complicated. You can simply just look at a triangle and simplify your approach. Tan is opposite divided by adjacent. Opposite divided by adjacent. So let's say opposite is 6 and adjacent side is 1. Hmm? Then hypotenuse is 1 square plus x square square root. So cosine of angle y is adjacent divided by hypotenuse. Adjacent divided by hypotenuse. Um, Next, dy over dx. Cosine square is just 1 over 1 plus x square. Just take square, whatever you have for cosine. Now you have a prefixed answer. You have derivative as a function of x. So we learned three derivatives of derivative of three different inverse functions. ln x, sine inverse x, tan inverse x. Now you can simply construct the derivative for other inverse functions. I'm not going to spend much time on this topic. Chain rule, computing derivatives of these functions. Right. Since we have another 45 minutes, I will teach you some other techniques to differentiate more and more complicated functions. I'll start with something called implicit differentiation. We already saw this while we are computing the derivative of inverse functions. Um, Implicit differentiation is a technique to differentiate equations, I would say. Implicit differentiation. Let me bring you back to our discussion about the vertical line test. Remember, sometimes graphs are not just graphs of functions, they are graphs of of equations. For example, the simplest example would be the graph of a circle. So get the graph of the unit circle. X squared plus y squared equals 1. To be a graph of a function, it must have a very special property. For every x value, should have a unique y value. That is the property of a function. For every x value, should have a unique y value. But on the circle, we have two different y values. If I set a value for x, I can get two values for y. For example, when x equals 0, y equals plus or minus 1. Not a unique solution, two solutions. So every x value gives me um, some x values give me more than one solution. Because of this is not a graph of a function. It fails the vertical line test. Now, the vertical line test says every vertical line intersects the graph at most at a point, not more than at a single point. But still, it is a graph of something, and still we can draw tangent lines and we can ask for the slope of the tangent line. Uh, One thing you can do is to convert this to a graph of a function. Um, so we have, you can see y square equals 1 minus x square. You can see y equals plus or minus square root of 1 minus x square. Now so you have two solutions. Let's say you decided to pick the positive solutions, only positive solutions. That means you only have positive y values, not negative y values. Positive y values means the top half of the circle. This is our x-axis. This is y-axis. Once we choose only positive y coordinates, we get this top half of the circle. This is now not a full circle, a semicircle. This is not what we were looking for. So we cannot just make it a function of some. We cannot just make it to a function by restricting y values. Because still somebody can come and ask you to find the slope of the tangent line to the circle at a lower point. Then you can, there must be a way for doing this. You can, again, you can choose the negative y values and solve the problem, but this is not the correct way of doing this. We have another elegant way for solving those problems. Just take the equation and differentiate the equation. derivative of x square with respect to x is 2x. Then differentiate y square. And if you think about this, square outside, this is a composition of two functions. The outer function is square function. Then inside we have y. We need y to be sort of a function of x. Our goal is to compute dy over dx. So derivative of y is dy over dx. So let's differentiate the outer function, then differentiate y. Equals derivative of 1. 1 is a constant, so derivative must be 0. Divide both sides by 2 and solve for dy over dx. So at every point, you can compute the slope of the tangent line using this formula. Negative x divided by y. No matter where these points are in the circle, as long as y not equal 0, as long as y is different from 0, we have a perfect answer. Y equals 0 is a problem because y equals 0 means you're at either this point or this point. At those points, the tangent line is horizontal. At this point, tangent line is horizontal, so it has slope has no meaning. It says slope is undefined. So at those 2 points, slope is not a well-defined thing. Therefore, still the formula valid, so y equals 0 in a way. So you can take any implicit equation and differentiate it. So this is what we call the implicit differentiation. Even to find the derivatives of inverse functions like y equals sine inverse x. We took this as x equals x equals sine y and differentiated both sides. That is another instance of implicit differentiation. Implicit differentiation really relies on the chain rule. Let me show you what I have in my notes about implicit differentiation. So implicit differentiation really talks about implicit versus explicit functions. See here, implicit function means an equation. Explicit functions are the ones we know, usual functions. We can differentiate when it has this explicit form very easily, but if it is not in the explicit form, that means if it is in the implicit form, we can use the implicit differentiation. Here's a good exercise. 3x squared minus 5y squared equals 12. 3x squared minus 5y squared. This is an implicit equation. Again, we can differentiate as we did in the other previous example. Take 3x squared, differentiate it. That should give us 6x minus 5 is a constant in front, so keep it in that way. Differentiate y squared, so square and then y. Let's see. So dy over dx equals 3x divide by 5 by y not equal 0. Hmm. Y not equal 0. Mm, These, ex- these examples are really simple, but at the same time, they expand our horizon. That means we now, with this implicit differentiation technique, we can differentiate even other things other than usual functions. Okay, I really like this exercise. This example number 2. Can you quickly solve this problem? Find the equation of the tangent line at the point 3, comma 3 for the implicit function. There's a typo. It must be corrected as implicit function. X cubed plus y cubed equals 6xy. I got one answer. Uh, So let me see. Uh, X to the third plus y to the third equals 6xy. So the implicit equation that we are interested in is now a cubic relation. And the point given is 3 comma 3. This is simple because for a function, if you know just the x coordinate, we can compute the y coordinate. But in an implicit equation, the case is different. For the same x value, we can have multiple different y values. For example, for x equals 3, if you substitute it into the equation, you get 3 cubed, that means 27 plus y cubed equals 18y. Now we know y equals 3 is a solution, so y minus 3 is a factor, and we have y square mm, mm, plus so this equation, it can have solutions. It may gives us some other y values. We already know this value, but in general, it can have other solutions too. So that is why this is not a function. This equation is not representing a function. It is representing an implicit function or simply an equation. Let's differentiate it. 3x squared plus 3y squared dy over dx. The other side is more interesting. 6 is constant in front, so we can keep it aside, x and y. So you can think of those are functions of x. So this is like a product. So we need to use the product rule. So x derivative of y is dy over dx plus y times derivative of x is 1. So on that side we need to use we had to use the product. Divide both sides by 3, and get x squared plus y squared dy over dx equals 2x dy over dx plus 2y. Now solve this for dy over dx. That be 2y minus x squared divided by y squared minus 2x. So this is formula valid as long as y squared is different from 2x. And so here we have a formula for the derivative. Let's evaluate it at this given point 3 comma 3. So when y equals 3, this is 6 minus 9, 9 minus 6. It's negative 1, right? So we don't know the shape of the graph. It may be something like this. We know slope of the tangent. The slope of the tangent line is 1 and it passes through the point 3 comma 3. So equation of the tangent line is yeah, let's use the point slope form because we know the point and the slope. So y minus 3 equals m times x minus 3. Y minus 3 equals negative x plus 3. So y equals negative x plus 6. That's it. I only got one solution, one answer posted in the chat, but that's perfectly correct. So yeah, this is how you solve it. The point is here we had something interesting. We had to use the chain rule. Uh, chain rule and sorry, product rule. Chain rule and the product rule. So you see, we can still do a lot of things. Not only this slope of the tangent line, we can do the equation of the normal line. So, uh, normal line would have slope 1. It passes through the same point, so y minus 3 equals now plus x minus 3, plus 1 times x minus 3. So y equals x. Y equals x. Right. Where is tangent line horizontal for the graph of this function? Graph of this implicit function. That's a perfect, very good question. Let's go back and see where we have horizontal tangent lines. To have a horizontal tangent line, so remember, so dy over dx is x square minus 2y over so 2y minus x, 2y minus x square. Two y minus x square, y square minus 2x. This formula works if y square different from 2x. The problem with y square equals 2x is at those points we'll have vertical tangent lines. The problem statements ask us to find the horizontal tangent lines. That means dy over dx equals 0. So we'll have 2y equals x squared. All right. At every horizontal tangent line, we'll have this property. The original relationship between x and y is this. And now we need to solve this relation and this relation simultaneously. So let's take this first relation and substitute in the second. Y is x squared divided by 2 to the third. Six x, y is x squared by 2. So we get x to the third plus x to the sixth divided by 8 equals 3 x to the third. Multiply everything by 8. Factor x cubed, x to the 3 minus 24 minus 8 is 16. So you have either from the first factor we say x to the third power equals 0. That means the only solution is x equals 0. Or the other factor gives you x to the third equals 16. If you take the cubic root of that, we have x equals 16 is 2 to the power of 4, right? So once we take the cubic root, this is 2 times cubic root of the 2. Two times cubic root of 2. And at this point, y equals x squared divided by 2. Now y equals x squared divided by 2. So square this number and divide it by 2. Divide by 2 makes and over here y equals 0. So this point and this point. We have 2 points with horizontal tangent lines. Yeah, the answer is written in a different form. In my notes, if you want, you can easily rewrite these answers just as a power of 2. So this is 2 to the power 4 divided by 3, and this is 2 to the power 5 divided by 3. So you should be very comfortable with algebraic simplifications and solving equations. We have done this for you have done this for a long time. When you are at school, you know simplifications. It is not the problem. You need to understand the mathematics, the derivatives, the process, the theory. You need to understand that part. Then the simplification is not that a problem. You can improve it by practicing, by solving things. But to understand the theory part, you need to think about it. You need to spend time and things what can go wrong, how one thing connected to another thing, how you can combine things and understand other things, how you can apply this so this method to some other problem. All right. Derivatives of inverse trigonometric functions. We have this is what we have. This is something we have done already, so you can skip that part. And still, there are some interesting some examples in that section. You can go through it. Composing inverse trig functions with other functions in various ways. Uh, Derivatives of exponentials and logarithmic functions. This is something we have already done, but in this section, a little bit more is happening. Not just e to the power x. This time, we are differentiating a to the power x. Here, a can be any number, not just e, any number, any positive real number different from 1. Then log b base x. Again, b can be a number different from traditional number, traditional base e. Uh, we'll go through this section next time, but in the meantime, you can go and study those by yourself. Logarithmic differentiation is another major topic. So we'll stop here. Um, Also, do not forget to submit your assignment on time. It will be due on this Friday, I think. You can go to our LMS page and look at it. Uh, as far as I know, everybody is in the LMS now, so it won't be a problem. Um, right. Do you have any questions? Okay, if you don't have questions, you can safely log out from the session. Right. Have a nice rest of the day.